Your permission to start the session?
Yes, good evening. You can start.
Good evening, everyone. A warm welcome to today's session. I'm Vaishnavi, member of Shivi Forensics. We are delighted to have you all here for an interesting topic that is color on the move, the hidden language of chromatography. Chromatography may look simple, but it plays a powerful role in chemistry and forensic science. Today, we'll get to understand how colors travel, separate, and reveal hidden information. We are honored to have with us Ms. Rashmi Dilip Kadu. Ma'am is currently working as a program coordinator and assistant professor in JSPM University. She has published research in reputed journals and has expertise in techniques like TLC, HPTLC, GCMS, UV visible, and HPLC. We warmly welcome you, ma'am. The session is all yours.
Uh, yes, good evening, everyone. I'll just check once if the slideshow will start.
Yes, ma'am, it is visible.
Slideshow is also visible, right?
Yes, ma'am.
Okay. Yes. Good evening, everyone. I'm Ms. Rashmi Kadu, Assistant Professor and Program Coordinator of UG at School of Behavioral and Forensic Sciences at JSPM University, Pune. So today we are going to study about the chromatography. The title of this particular presentation is Colors on the Move, the Hidden Language of Chromatography. So, first of all, if we say chromatography and if we break down this word can be broken into two terms. One is chroma, another is graphy. Chroma means colors and graphy means to write. So, first, this chromatographic technique was invented in the year 1901 by a Russian botanist Michael T. Sweat. So this Michael T. Sweat, he had used plant pigments and he had separated out the pigments present in these plants like chlorophyll, and on that basis he had also further got the Nobel Prize for this particular invention. Further, in 1952, A.J. Potter Martin and Richard Lawrence Milliston Synge, that is Martin and Synge, they had also won the Nobel Prize for partition chromatography. We will study about what this partition chromatography and other types of chromatography in the upcoming session. So first of all, chromatography. As I said, it's a Greek word, and if we break down, this is two terms. One is chroma, another is graphy. Chroma means color, and graphy means to write. It is a powerful analytical technique which can be used for separation. We can also use it for purification, and we can also use it for the identification of different compounds. So basically, it is a method of separating components where the substances can be either distributed between two different phases. So here there are two different phases which are used. One is stationary phase, another is mobile phase. Stationary phase, as the name suggests itself, stationary means to stand or to be stable. Station, like railway station or bus station, you might have heard. So station means where everything is being stopped. Mobile phase means the thing are moving. So as we say, mobile vans or mobile forensic laboratories, similarly mobile phase means the phase which is moving. So these are the two types of phases which are mostly used in chromatography, and all the separation is based upon these two phases only. So chromatography is used by forensic scientists for analysis of different evidences, which we will see further. So there are core principles of this chromatographic method. Two chromatographic principles are main important principle. One is affinity, another is distribution. Distribution means whenever we are separating any sample, basically through chromatography we can separate out the mixture of sample. So whenever we are separating out these samples on the basis of its affinity towards either stationary phase or towards mobile phase. Affinity means attraction. So if the sample is polar in nature, it can go towards the stationary phase or mobile phase depending upon what stationary phase or mobile phase you have chosen. I would like to simplify this. So as I said, there are two phases. One is stationary phase and another is mobile phase. Now there are two terms as well, polarity and non-polarity. Polarity means having more number of ions, okay, H positive ions or OH negative ions. So if more, in simple terms, if I say if more number of ions are present, then that particular solvent can be polar. And if less number of ions are present, then that particular solvent can be non-polar in nature. So if your mobile phase is polar and sample is also polar, then this sample will have an attraction or have an affinity towards the mobile phase. If your sample is non-polar and your stationary phase is also non-polar, then the sample will have affinity or attraction towards the stationary phase. Now, distribution. Distribution means basically partition. So whenever a sample is traveling from both stationary phase and mobile phase, whenever a sample is being interactive with the stationary phase and mobile phase, at that time, this sample will get distributed between both stationary phase and mobile phase. So that particular principle is basically distribution principle, or we can also say it as partition principle. One more terminology which is very important here is retention factor. Retention factor, although it is mentioned here, but we will discuss it in the upcoming slides. Now, classification of chromatography. Chromatography is divided into different types depending upon different bases. So one of the bases is on the basis of separation principles. So on the basis of separation principles, chromatography is divided into 5 types. One is adsorption, another is partition, third one is ion exchange, fourth is affinity, and fifth one is gel permeation. Now among these, partition and affinity we have already seen, because these are core principles on which almost every type of chromatography can be dependent. Now what is adsorption? You might have heard about absorption till now, ABSORPTION, right? Absorption. So like whenever you take one cotton, dip it into water, what happens? The cotton will absorb the water, right? Now what do you mean by adsorption? Adsorption means that on any particular surface, the substance is going to be adhered. Adhered as in it will just stick to that particular surface. It won't get absorbed. It will not go inside that particular surface. It will be adhered, or it will be on that particular surface. For example, whenever you eat samosas on a plate, let's say you have a paper plate on which you have had a samosa. Now the oil which is present in that samosa gets absorbed in the plate. However, the particles of samosa or the chutney, or we can say the aloo bhaji, everything stays on that particular surface. So that is called as adhering, and this process is called as adsorption. Okay. Third principle is ion exchange. So on the basis of ion exchange, first of all, what do you mean by ions? Whenever we take any sample and dissolve it in solution, it converts into its ionic form, right? For example, if I talk about water, ionic forms of water, ionic form of water will be, the formula is H2O, so it will be H plus and OH negative ions, right? So ion exchange means here, on the basis of the ions, the separation is going to happen. Okay, it means that we'll have an anode and we'll have a cathode. Two electrodes will be there, anode and cathode. Cathode is always positively charged, anode is always negatively charged. And in our sample, we will have ions. We'll have positive ions, we'll have negative ions. Now, all of us know that the positive negative attracts each other, right? So if we have negative ions, these will get attracted towards the cathode. If we have positive ions, it will get attracted towards the anode, and on that basis there will be the separation of these compounds. So that is basically ion exchange chromatography. And fifth one is gel permeation or size exclusion chromatography. Now in this particular chromatography, the stationary phase which we use is made up of gel. Okay, so here stationary phase itself will be made up of gel. And now all of you know that the gels are always having pores. So there can be large number of pores, there can be small number of pores. So now the mixture of sample which you have, if you are separating out this mixture of sample from this gel, if the molecule size is more, then that will travel faster here because it will have lesser resistance. If less resistance is there, there will be faster separation. So bigger molecules will be separated first. And then smaller molecules, since there will be pores in this gel, when these smaller molecules are traveling, they'll get resistance, they'll get stuck in these holes, and that is why they will move slowly. So that is the reason smaller molecules will come out with the slower time, as well as at last these smaller molecules will come. Okay, so 5 types of classifications we have studied. One is adsorption, where sample is adhering on the surface. Another is partition, where the sample will get distributed in the stationary phase as well as mobile phase. Ion exchange, where the samples in the form of ions will get attracted towards the anode or cathode depending upon the charges present on it, or we can say separation will happen on the basis of charges. So that is ion exchange chromatography. Fourth one is affinity, means attraction of sample towards the stationary phase or mobile phase. And fifth one is gel permeation or size exclusion. Gel permeation, because gel is permeating or is permissible for some molecules to pass through it. Size exclusion, because on the basis of size, these particular samples are getting excluded or getting separated. Moving on forward. Now, on these different principles, there are different types of chromatography. We have column chromatography, paper chromatography, thin layer chromatography. When we say column chromatography, in that also, or instead of saying column chromatography, we can say liquid chromatographies. So in liquid chromatographies also, there are certain types like gas chromatography or high performance liquid chromatography. So let's see a little brief about these type of chromatographies. First one is paper chromatography. So the principle of paper chromatography is based upon both partition and adsorption. Okay, so in paper chromatography, there can be both the principles applied. When will it be partition? Now, here paper acts as a stationary phase. Okay, now on this paper there will be this paper basically is made up of cellulose. We use usually Wattman filter paper. Wattman number one represents the size. So there are different sizes of Wattman filter paper available, and the least particle size is present in the Wattman filter paper number 1. Okay, so that we basically use. Now this Wattman filter paper is made up of cellulose. Now what happens is, when this cellulose paper comes in the contact with the atmosphere, and if this atmosphere contains moisture, so the cellulose will absorb this moisture and it will form a layer, a thin layer of liquid. So that is why now the stationary phase, that is paper, which is actually solid, but now since it is made up of cellulose and absorbing the moisture, it will coat a liquid layer, and that's why it will become a liquid stationary phase and not the solid one. Okay. Here mobile phase will also be liquid only, so that becomes liquid chromatography. And whenever there is liquid chromatography, the principle applies will be partition principle. Okay, so here the sample will be distributed between stationary phase and mobile phase. Now when we say paper adsorption, so in paper adsorption, here on this paper there will be a thin layer of silica gel. Either we use silica gel or alumina. So a thin layer of this silica gel or alumina will be coated. Impregnated means basically coated on the paper. And then that paper will act as a stationary phase. So now this will be a solid stationary phase here, and mobile phase will be liquid. So that becomes the solid liquid type of chromatography. Paper chromatography is also classified into 5 different types. First one is ascending method. Okay, now in ascending method, what happens is we will have one Wattman filter paper. Okay, like in this particular image, you can see if we let's go horizontally. Okay, let's imagine that this horizontal paper is present in the vertical format. Okay, now what happens here, you can see the y component. So in this paper, what you have to do is you have to spot the sample here at the y component. When you have spotted the sample, now separately you have to prepare a mobile phase. Okay, this mobile phase will be present in one solvent chamber, and now you will place this paper in this solvent chamber. What will happen? The sample will travel along with the mobile phase. And then why is it traveling? Due to capillary action. Okay, because it's a paper will have a capillary action also. And on the basis of this capillary action, the sample will travel from the down towards the upward position. Means it will be a ascending method. Now when you reverse this paper, means basically if you keep spot the sample at the top, and the solvent will also run from the top to bottom, at that time the separation will also happen from the top to the bottom, and that method will be called as descending method. Next is one dimensional method. Now in one dimensional method, what happens is we take a paper, Wattman filter paper again. We will take a Wattman filter paper. At one corner, we will place the sample, or we will spot the sample. Now when this paper is placed in the mobile phase, this particular analyte or sample which we have spotted in the corner will travel in the upward position. So now when it is traveled in the upward position, it will travel only in one direction, one dimension. That is why it is called as one dimensional chromatography. Now the same paper of one dimensional chromatography, when you turn it over as in, since you have now spotted the sample in one corner, let's say on the left hand side, you have spotted the sample. Now what you will do is, this left hand side sample have traveled in the vertical format. Now you turn it over. So I will just give you one example here. If you are able to see it on the screen, I have this paper, okay, and on this paper I have spotted the sample in one corner. Okay, in this corner I have spotted the sample. Now this sample is traveling upward. Okay, so it has traveled upward, it has gone in the one direction, means one dimensional chromatography. Now the same paper you can use for the two dimensional chromatography also. So what you will have to do is, you will have to turn this over. You have turned it. Okay, earlier it was like this, now you have turned it over. Now you have your sample here and the separated components here. Let's say you have one sample, that is sample A, and the separated components A1 and A2. Okay, let's say you have one sample here, that was A. Okay, in one dimensional you had taken A sample. In the mobile phase it traveled, and you have got the separation A1 and A2. Now you need to turn it over. Now you have A1, A2. Three samples are there, separated, two components separated, and one sample, mixture of sample which we had taken. Now to place this particular paper again in the mobile phase. Now like this only, Let's say this is the mobile phase. In the mobile phase, like this only, you will place the paper. Once you have placed this paper, now these three components, they will travel upward. These three components, they will travel upward along with the mobile phase. So now they will also give you certain separation. Since you are separating it twice, you might get again B or C separation, here B1 and C1 separation, or you can say even D separation. So your A component, that also again got separated into D. Your A1 component got separated into B1 and C1. Your A2 component got separated into B2 and C2. So like this, you can get more separation in two-dimensional chromatography. So whenever there are huge number of or huge mixture of samples present in such type, or at that time mostly we use two-dimensional chromatographies also. Then another type or fifth type we can say is radial method. Now in radial method, what happens is we take a circular Wattman filter paper. Okay, the Wattman filter paper will be present in the circular form. So in the circular form, here I have one dhakkan. I will just show it to you all. Okay, so this is present in the circular form. Now we will cut down the paper from one side. Okay, from here we will cut down the paper. Now once we have cut down the paper, now what we do is, here at the center we will spot the sample. Okay, the sample will be spotted at the center, and then there will be a wick as in a thread. Okay, a normal thread which you use for the time supplements in your exams. Okay, so that type of thread is called as wick, WICK. Okay, so this wick you will put one end here where you have spotted your sample, another end will be put in the mobile phase. You will have a separate beaker. In that beaker you will have your mobile phase, and in that another end of the wick will be put. So that is called as radial chromatography.
What the fuck?
To happen. So that is called as radial type of chromatography, radial type of paper chromatography. So these are the five different types: ascending method, descending method, one dimensional, two dimensional, and radial. Mostly we use ascending method, and sometimes we use two dimensional paper chromatography. Now let's see the thin layer chromatography. Now, thin layer chromatography is developed by Stahl. Okay, there is a scientist called as Stahl. In 1958, he had developed thin layer chromatography, mostly for the separation of drugs, plant pigments, explosives. We use thin layer chromatography. Now, here in thin layer chromatography, basically we will have a aluminium foil, or we can say even a glass slide. Okay, so a glass slide is present on which we coat a layer of silica gel. Okay, now here the first step which we have to do is, we have to take a beaker and prepare a slurry of silica gel. Okay, like how we prepare our dough for atta, for chapati. Okay, so in similar manner here we have to prepare a silica gel slurry, or it is similar with the preparation of your omelets. Okay, like we take egg, add it in the vessel, and then we just mix it using a spoon, right? Similarly here what we do is, we take silica gel and water. So silica gel and water will be taken in the ratio of 1:2, means one part of silica gel and two parts of water. So that we will take in a beaker. we will mix it using a glass stirrer. Okay, now when we are mixing this slurry, we need to make sure that there are no bubbles present, there are no lumps found present in this particular slurry. And then once you see a nice thin slurry prepared, now you have to pour it onto a plate. Okay, so you take a glass slide. On this glass slide, you pour the silica gel slurry. Now, when you are pouring this silica gel slurry, this slurry should be spread throughout the glass plate. You need to make sure that you are making a thin slurry or thin coating on that particular glass plate. It should not be thick. The thickness should be 250 micrometers, or you can say 2.5 mm. Okay, and also again in this particular coating, there should not be any bubble formed. There should not be any breakage. So you need a uniform in order to activate it oven for 1 hour at 110 degrees Celsius. Now, what do you mean by activate and why 110 degrees Celsius? 110 degrees Celsius because we are using water in the silica gel slurry. The boiling point of water is 100 degrees Celsius. So what we want? We want the coating to be completely dried. So in order for water to get evaporated, we need its boiling temperature, that is 100. So that is the reason why we keep the temperature at 110 degrees Celsius. Now, what do you mean by activate? Activate means basically once we keep our plate at 110 degrees Celsius for 1 hour, entire water or entire moisture will get evaporated, and our plate is now going to be ready for the analysis. Okay, so that means basically we are activating our plate. Now, once we have activated our plate, now we will prepare a sample separately. How do we prepare a sample? We take the sample, we check its solubility. Let's say, for example, we have taken sugar sample. Now, sugar is solubilized in water, right? So we can take mixture of this sugar and water, or if you want to take science, we have a spinach sample. Okay, solubilized in chloroform and also hexane. Okay, so now since it is solubilized in both, shall we use both the solvents or we can use only single? So we can use single solvent also, we can use both the solvent also. Now what happens? Every sample have polar as well as non-polar components. Okay, I have described polar and non-polar earlier. So polar and non-polar components both are present in most of the samples. Now polar components will be solubilized in polar solvents only. However, non-polar components will solubilize in non-polar solvents only. So here when we say hexane or chloroform, even acetone can be used. So acetone is polar in nature, hexane is non-polar in nature. So the non-polar components of spinach will get solubilized in hexane. However, polar components of spinach will get solubilized into acetone. So in such type of samples, we can use mixture of solvent. We can use acetone also. We can use hexane also. So both of them we will take in the spinach sample. We will solubilize it. Once the spinach sample is solubilized, now using a capillary tube, we will take the small amount of sample, and then exactly above 1 centimeter. Again, I will take this paper. Let's say this is our glass plate, TLC plate, or plate which is coated with the silica gel. Now, here is the bottom of this plate. You will draw an imaginary line, means you have to imagine that this is 1 centimeter distance. So at 1 centimeter distance, exactly at the center, you have to spot the sample using capillary tube. Now how are you going to spot this sample? Exactly at the 90 degree. Okay, you should exactly spot this sample at the 90 degree. Okay, like this. At 90 degree, you are going to spot the sample. Why 90 degree? Why not like this, tilted, or any acute angle? Because you want the entire sample present in your capillary tube to go into that or spot into the plate. Okay, now why in the center? Why to spot the sample in the center? So what happens sometime, since we are doing this spotting manually, we might shiver, and there is chance that our sample might get a little bit here or there. Also, when we are once we have spotted the sample, we need to wait for some time so that the samples get dried, and then we will keep this particular sample in the mobile phase. Okay, we will prepare a solvent system separately. Now this solvent system again can be of two types. One will be isocratic, another will be gradient. Iso means single, so isocratic means you will use only single solvent. Okay, and if we say gradient, gradients means mixture of solvent. Okay, so depending upon your sample, here we have taken example of spinach, which has both acetone and hexane solubilized in it. So similarly, for separation also we can take hexane and acetone ratio in the 5:5 ratio or 7:3 ratio. Okay, and we will take 7 ml of hexane here, 3 ml of acetone in one particular beaker, and in that way we have prepared our mobile phase. Now the plate on which we have spotted the sample, we will keep this in this mobile phase. Okay, now what happens when you are keeping this plate in the mobile phase? Sometime you are, again as I said, doing it manually, so you are shivering. So sometime your mobile phase can travel from here more, here less. So what will happen if you spot your sample in corner? There are chances that the sample travels in some, like this, in this way, left hand side or towards the right hand side. So if you spot it in the corner, the traveling area, the sample will get very less. So because in order to remove this, or in order to prevent this, we spot the sample at the center. Okay, whenever we are spotting the sample at the center, even if it is going towards left side or right side, the sample will get more area to travel through the plate. Okay, so that is the reason you should always spot the sample in the center. Now you have spotted the sample in the center using capillary tube above 1 centimeter distance. Now you have to take this particular plate and keep it in the solvent system. Now once you have kept the plate into the solvent system, this is called as development. Now your sample will slowly travel with the mobile phase. If it has more affinity towards mobile phase, it will go more towards the mobile phase. If it has more affinity or attraction towards the stationary phase, it will move slowly along with the mobile phase. Okay. Now, as we have taken spinach sample already gives a visible separation. Okay, so in this particular case, visibly you will be able to see the separation, but there are certain components which do not give you a visible separation, like there are certain drugs. So in that case, what you have to do is, either you will have to prepare visualizing agents, means you will have to prepare separate reagents which you can spray onto this plate, and then there will be a color reaction in between the sample and the reagent, and then you will be able to see the colors of the sample separated. Or you can visualize it under UV light, so either short UV or long UV on that wavelength, means 254 nanometer or 350 nanometer. You can observe the separation. Sometimes you can also use iodine vapors, but iodine vapors are mostly used when we are doing paper chromatography. So now, what are the applications or advantages of TLC? Key applications are, we can separate out the plant pigments or alkaloids. We can do the poison analysis from visceral samples. We can separate out the explosive materials. Drug examinations like benzodiazepine, barbiturates, amphetamines can be done. Pesticides or sulfonamide analysis can also be done using thin layer chromatography. And what are the advantages of TLC over paper chromatography? So first one is it give you a sharp separation with less diffusion. Means here the sample will not get diffused and you will get a proper separation. It provides you faster analysis than the paper chromatography. It requires very small amount of sample. It can tolerate the high temperature, and the sensitivity of detection is increased in TLC over paper chromatography. Now, as I had mentioned previously, that we will also discuss about the RF in the upcoming slides, right? So let me see how I can. I want to draw it here. Okay, I don't think I will be able to draw anything. Okay, let's move forward, and later I will show you how what is RF value and how do we calculate it. Next is high performance liquid chromatography or even column chromatography. So I had mentioned previously, when we are studying about chromatography, there are different types: paper chromatography, thin layer chromatography. There is liquid chromatography. In liquid chromatography, we have column chromatography, high performance liquid chromatography, and gas chromatography. So let's see these three techniques in a brief. See, these are very long techniques. Each technique will need 1 to 2 hours to be explained, but we will see in very brief or a summary of these particular types. So first one is column chromatography. Here, as the name suggests, we use a column. Okay, so a column is used in which these columns will be packed with the stationary phase. Now, earlier when we studied about paper or TLC, it was just a paper which was acting as a stationary phase, or it was a glass plate having a coating of silica gel that was acting as a stationary phase. Here, the column will have a packing material. Mostly silica gel or alumina is used as a packing material. So column will be packed with these particular materials. Columns can be of 10 to 30 centimeters of length, and it can be of 4 to 5 millimeters. So when you want to separate out samples using column chromatography, the separation which you get will be in the 3D form. Okay, so that is why there are two again types of chromatography. One is planar chromatography, another is column chromatography. Planar chromatography is two-dimensional or 2D form, paper and TLC. Column chromatography is three-dimensional or 3D form, which includes mostly HPLC and GC, high performance liquid chromatography and gas chromatography. So in high performance liquid chromatography, why it is said high performance? Now, instead of high performance, it can also be called as high pressure. So why that? Because here we use a pressure to increase the performance of the separation or the analysis. So whatever analysis we do, this analysis will be done with the high amount of pressure. The pressure here applied can be of 5000 Pascal. Okay, Pascal is the unit of pressure. So 5000 Pascal is the standard amount of pressure applied in HPLC system. So here what will happen is there is column, analytical column. In this column will be packed with the packing material. Okay, and now first there will be mobile phase. Okay, separate components are there. First there will be mobile phase. Again, isocratic means single solvent, or gradient means mixture of solvent. You can use any of it. Okay, mobile phase will be there. Mobile phase will travel and then it will go towards the column. Before going towards the column, this mobile phase will go through the pump. Okay, Why pump is needed? To provide the pressure. Okay, pump is applied here to provide the pressure. Now after pump there will be sample injector. So sample can be either injected manually or it can be injected automatically also. Okay, so manual sample injectors or automatic sample injectors are used. Now once you have injected the sample, this sample will now travel through the column. Okay, now once the sample travels through the column, it will travel with the mobile phase also. So when this sample gets separate out, if it is a mixture of sample, let's say it was a sample of your sabzi. Now you know that sabzi contains onion, tomato. Then let's say it was aloo sabzi, so there is potato also. Okay. Now what will happen when you are separating out this mixture? First, the onion will come out. Then that will once it is traveling through the column and getting detected in the detector. Obviously, in order to detect here there will be a detector since it's a sophisticated instrument. Okay, so onion will get detected first since it has traveled first. Then later, let's say tomato traveled, so tomato will get detected. Then let's say the potato traveled, so potato will be detected at last. Now for these onion, tomato or potato, it is taking some time to travel through this column. Okay, let's say this was the column, and from this column this onion, tomato, potato, everything was traveling and getting detected at the end. Okay, so this time which is taken by this onion to travel, or time taken by the tomato to travel, or time taken by the potato to travel, this time is called as retention time. So let's say after 2 minutes you got potato, 2 minutes you got onion detected. That will be the retention time of onion. That will be 2 minutes. After 4 minutes you got tomato, so 4 minutes will be the retention time of tomato. After 5 minutes you got potato, so 5 minutes will be retention time of potato. So here the detection is happening in terms of retention time, which will always be measured in the form of minutes. Further, next is gas chromatography. Now, the name suggests itself, in gas chromatography, gas will be used. Okay, gas chromatography was developed by James and Martin in the year 1952. So here, gas chromatography is mostly used for volatile components. Yes, when we discuss about HPLC, HPLC is used for the detection of non-volatile components. Okay, non-volatile means such components which cannot be evaporated. These type of components or samples can be analyzed using HPLC. And volatile components means such components which can get evaporated. So using gas chromatography, we can separate out the volatile components. Okay. Now here, as in HPLC we had discussed, mobile phase is used. Here as a mobile phase we are using carrier gases. Okay, carrier gases means mostly inert gas, or we also call it as zero order gas. These type of gases are used as a carrier gas. So helium, argon, neon, xenon, these are the zero order gases. Along with that, nitrogen, hydrogen or argon methane mixture. These gases are also widely used. Mostly the gases which are used as a carrier gas are helium, nitrogen and hydrogen. Now here also there will be columns, and these columns will be packed with the stationary material. Now there are different detectors used in gas chromatography. So it can be either thermal conductivity detector, flame ionization detector, or electron capture detector. Will not go in very much detail, but just to give you an idea, thermal conductivity detector will detect the thermal nature of the sample. So detection will happen on the basis of thermal conductivity of that particular sample. In flame ionization, on the basis of flame, the sample will get ionized due to the flame. Okay, now this flame can be of argon gas. Okay, and once the sample is ionized, that will get detected in flame ionization detector. Third one is electron capture. Now here the sample, when it is traveling, sample will emit the electrons, and the number of electrons emitted by the sample will get captured by the electron capture detector. Okay, here the main thing which are important in gas chromatography, first is carrier gas. Okay, so carrier gas we use stable zero order gases or inert gases. Then second thing is columns. So we use packed columns. Now before column and after carrier gases, there is also sample injector. Here also there is manual sample injector as well as auto sample injectors. Any one of them can be used. Mostly we are nowadays using auto sample injectors. Now sample will get injected. Here the important role is played by the column, because column we have to keep it at certain temperature. So what temperature we have to keep? Because our sample, it can be liquid also, it can be in the gaseous form also. Okay, so if it is a liquid sample, it should turn into gas in order to travel through the column. Okay, because we are at the end detecting the gas here. This is a gas chromatography. So that's why the temperature of column needs to be set at the boiling point of sample. For example, if you are analyzing ethanol, now ethanol is volatile in nature. It has a boiling point of 78 degrees Celsius. So this ethanol will travel through the column. Column temperature will be set at 78 to 80 degrees Celsius. So when we are keeping it at 78 to 80 degrees Celsius, automatically ethanol will get converted into vaporized form. And this vaporized form will be further detected in the detector. So that's why column temperatures are very, very important here. Now, uh, I will just stop sharing and share the screen again, because as I said, I need to draw something. How do I do it? Can I have a whiteboard here in this? No, I'm not able to have a whiteboard. Mm, are you able to see this?
Yes, ma'am.
Okay. So I will just draw something and then I will show. So as I said, we need to discuss about the RF value or retention factor. So we have spotted the sample. Okay, this is the paper. Let's say this was the Wattman filter paper we have taken. You can see a spot. So we have spotted the sample. Now when we keep this paper in a mobile phase, this sample will get, it will travel. Okay, sample will travel in upward direction along with the mobile phase, and then it will get separated. Okay, so let's say we have got two separations. The sample which we had spotted was sample A, and the separation which we got, let's say that was B and C. Okay, I hope you are able to see. So now you can see the sample where we have spotted, that is A, we also have drawn a line that is called as baseline. So on baseline, exactly at center, we have to spot the sample. Now we have spotted the sample. We have kept this particular paper in mobile phase. The sample has been separated out into the two components B and C. Okay, and you can also see a line here. So this line represents that our mobile phase traveled this particular to this particular level. Okay, because we have kept this paper in mobile system, mobile phase system. So mobile phase will also travel along with the sample, right? So whenever the mobile phase travel 3/4, we have to take out the plate. Okay, even if it is paper, even if it is TLC plate, we have to take it out. Why? Because if we do not take it out, the sample as well as the mobile phase will overrun. And if it is overrunning, you will not get proper separation. So that's why whenever it is at the 3/4, you have to remove this paper or TLC plate. Now, when you have removed, now you have to calculate the RF value or retention factor. Retention factor means for how long, how much distance the sample was present in this particular paper or in this particular plate. That is retention of it. Okay, so how do you calculate? There is a formula of retention factor. Okay, there is a formula of retention factor. This formula is distance traveled by the solute. You can see here distance traveled by the solute, or we can say sample, upon distance traveled by the solvent. So you see, it is basically a ratio of distance traveled by solute to the distance traveled by solvent. Distance traveled by solvent means basically this particular distance. So now how do you calculate this distance? You have to take this baseline. From baseline to the distance traveled of the mobile phase. This is your mobile phase. This line which we have marked here, till here the mobile phase was traveled. That we call it as solvent front. Okay. So from baseline to the solvent front, we are going to measure the distance. Let's say this distance was 10 centimeters. Okay. Now let's say this distance was 10 centimeters. Now from A to B, means your A component have been separated out into two different components, component B and component C. Okay, now how do you measure the distance of component B and C? So from A, that is from your baseline, you have to take the measurement, okay, from baseline till the component B. Okay, so let's say that particular distance was 2 centimeter, and then you will also take the distance of C. Let's say that was 5 centimeters. Okay, again I am repeating. First, we have taken a baseline. From baseline till the mobile phase where it was traveled, we have measured the distance, that was 10 centimeters. Now, component B and C were separated out. So we will measure the distance of component B from the baseline and component C from the baseline. Component B was 2 centimeters, component C was 5 centimeters. So what will be the retention factor for component B? So as we say, the formula of RF, to calculate RF value, is distance traveled by solute upon distance traveled by solvent. So it will be 2 divided by 10. 2 was the component B and 10 was the solvent traveled distance, right? So it will be 0.2 centimeters. Will it be centimeters? Now since here there is a catch, since both are the distance, the ratio which we have taken is of distance. Centimeter will get cancelled with each other. Okay, both the centimeters will get cancelled with each other, and only you will be having the numerical value. So here 0.2 will be the RF value of B component. Okay, so always remember, RF value will never have any unit. It does not have unit. It will always be only a value, and this value will always range in between 0 to 1. Why in between 0 to 1? It can never be 0, it can never be 1, because if it is 1 means both your sample and your mobile phase has traveled at equal distance. If it has traveled at equal distance, means there is no separation happened, right? If your RF value is 0, it means neither your solvent traveled, neither your sample traveled. It means again no separation happened. That's why RF value will never be 0, it will never be 1. It should always be in between 0 to 1. Okay, Now for component B it was 0.2 centimeters. Let's see about component C. So for component C, it will be 5 divided by 10. 5 ones are 5, 5 twos are, so it will be 0.5. Okay, so RF value for C component will be 0.5. I hope you have understood the concept of RF value. Now, moving on towards the application of chromatography in forensic science. So, first of all, in the toxicological analysis. So, in order to determine blood alcohol concentration, okay, from the blood samples, we extract out the alcohol, and then using the gas chromatographic method, we can determine the blood alcohol concentration. Volatile poisons, drug screening, plant toxins identification, all of these is possible to analyze in biological samples using gas chromatography as well as HPLC. Okay, plant toxins can be analyzed using HPLC. Wherever there is volatile component, that can be analyzed using gas chromatography. We can also do the explosive detection. So through HPLC, we can analyze PETN, TNT, HMX. These are some potential explosives which are found in any kind of explosive cases or arson cases. Okay, so these basically gives you retention time between 1.4 to 3.1 minutes. So using again HPLC, we can separate out these explosives. Then we can do drug analysis even by using TLC, HPLC, or GC. Amphetamines, barbiturates, benzodiazepines, and different alkaloids. Alkaloids are present in most of the plants, so that can also be analyzed using chromatography. We can also do the environmental testing, like if we want to analyze pesticides. Now in most of the poisonous cases or suicide cases, pesticides are used because all of us know that India is a agricultural country where agriculture is mostly present as an occupation of Indian people, and they have easily available pesticides or insecticides with them. So most of the time whenever these farmers are uh, if they are committing suicide, the reason behind that or the poison behind that is mostly pesticide or insecticide. So in such cases chromatography can be used for the separation of it. Then petroleum products, in order to separate out the petroleum products, we can use gas chromatography. And also for the detection of PCB in environmental samples, we can use the chromatographic method. So chromatography is very much helpful in forensic science. From whenever we say toxicology division, in the toxicology division, whenever there is any sample, once that sample is extracted and after doing the preliminary examination, the first thing we do is either paper chromatography or thin layer chromatography, and then only we move forward with other sophisticated instrumentation. Thank you. That is all, guys. So there are no questions, is it? Everybody understood everything?
Yes, ma'am. Thank you so much, ma'am, for the insightful session. And thank you everyone for joining us today's evening. And have a great night ahead. Thank you so much, ma'am.
Thank you, Vaishnavi, and thank you, Shivi Forensics, for giving me such an opportunity. Thanks to all the participants who have joined this particular session. I hope all of you have got a little bit of what chromatography is. If you want more details about it, you can contact me anytime on LinkedIn, and I can share the more details about this particular.
Thank you so
Thank
much,
you,
ma'am.
ma'am.